And this talk ended basically on time, and so we can move on to the next talk by Sarah Morell. Giacomo, Sarah, would you share your screen?
So everyone can see my slides and that you can hear me?
Yes, so let me first introduce you. Yeah, I'm very much looking forward to hear the talk by Sarah Morell, and she's currently a PhD student in Martin Scutella's group. And yeah, Sarah is talking about single source unsplittable flows with arcwise lower and upper bounds. The screen is yours.
Thank you, Britta, and thank you all for being here. This is actually joint work with Martin, my advisor. So let's start. The single source unsplittable flow problem has been introduced by Kleinberg in '96. We are given a digraph that I denote by D. So V is the vertex set and A is the arc set. And then we have a single source S and K commodities that each have a sink node Ti and an associated positive demand Di. And then the task is to route each demand Di unsplittably. So it means that for each commodity, we choose a single path from the single source S to the sink Ti, and the whole demand Di is routed along this path. So as you can see here in this example, we have the single source here on the left-hand side. And for example, if we have a look at this demand, so demand is equal to 4, we choose this orange path here, and the whole demand is routed along this path. This is the case for all capacities we have here. So we have another commodity here, and a new commodity here. If we are given our capacities, this problem is NP-hard. And in what follows, I will always assume that each node in the arc in the graph lies on an STI path for some commodity. And whenever I talk about flow, I mean flow satisfying the given demands you want to decay. Okay, so this is the general problem, but it's not the problem we're looking at today. The problem we're looking at today has been motivated by Dienet, Skak, and Gumans in '99. They've actually been looking at fractional, or the problem where we are given a fractional flow. When I say fractional flow, it just means an arbitrary flow in order to distinguish it from unsplittable flows. So for a given arbitrary flow X, they show that there exists an unsplittable flow Y satisfying arcwise upper bounds. So it means that the flow that we get does not differ by too much from the given flow X. And in particular, we want that on each arc, we have an upper bound of XA plus the maximum demand. This is the upper bound we want to have on each arc. This is tight, as you can see in this example. So if we have like small fractions of a unit demand going through a lot of arcs, we need to choose one arc in order to get an unsplittable, so one path in order to get an unsplittable flow, which means that we need this upper bound, this additional part D max for this upper bound. Okay, so we are interested in modifying flows into unsplittable flows while they do not change by too much. So it might be interesting to not only look at upper bounds, but also arcwise lower bounds or arcwise lower and upper bounds simultaneously. And this is exactly what we will do today. So we will first come to lower bounds. So we show that for a given flow, there is an unsplittable flow satisfying arcwise lower bounds. So on each arc A, the unsplittable flow Y, the flow value is at least XA minus the maximum demand. And in this talk, I will actually focus on the proof of this theorem, as it's a, we will look at nice augmentation steps that are quite easy, and we will see that we can modify an arbitrary unsplittable flow into an unsplittable flow with this additional property via those very simple augmentation steps. And as a second part of the paper, we could actually show some upper and lower bounds simultaneously. First of all, we have a special case where all demands are actually integer multiples of each other. And then we can show that for a given flow X, there is an unsplittable flow Y such that those tight upper and lower bounds are satisfied. So the flow on each arc A, so YA, is between XA minus Dmax and XA plus Dmax. And for arbitrary demands, we actually lose a small factor of 2. So for arbitrary demands and a given flow, we get bounds of XA over 2 minus Dmax and 2 XA plus Dmax. This proof relies on an iterative rounding procedure. We will come to this like very shortly, but I mainly focus on the first part in this talk. Okay, so let's move on to the flows with arcwise lower bounds. What we first of all need is this definition of reachability. So we always work with 2 flows. So we have a given arbitrary flow X and an arbitrary unsplittable flow Y, and both satisfy the same demands. And if I have a commodity I, a node is reachable for this commodity with respect to the unsplittable flow if, first of all, this node lies on the path we've chosen for commodity I. So as you can see here, my notation is PIY. Of course, the paths we've chosen in order to satisfy the demands depend on the unsplittable flow we have. So for each commodity, we have chosen a path PI in this unsplittable flow Y. So our node lies on this path, and all arcs on the SV subpath of this path we've chosen actually satisfy this property here, that the flow YA is at least XA. Here's a small example. You can simply quickly have a look. So we have the fractional flow on the left-hand side and an unsplittable flow on the right-hand side. Both satisfy the 2 demands that are given in the graph. You can see that this node here, for example, with respect to the given unsplittable flow, is an example of a reachable node. As we can reach it, it lies on the path we've chosen actually for this demand, and 1 is at least 1/2. So this is an example of a reachable node. This one here is not. It is somehow we have those 2 arcs here that have flow YA at least XA, but it's not actually a subpath of a commodity. So the only path we could choose in order to reach this node is actually the orange one, and there we have an arc that does not satisfy the property. I hope that this definition is clear of reachability, what it means, because we need it now for those augmentation steps. We call them lower bound preserving augmentation steps, which again are given flows X and Y. X is an arbitrary fractional flow, Y is an arbitrary unsplittable flow, and we let V be a reachable node for some commodity I with respect to the unsplittable flow. So what are we doing now for this augmentation step? As you can see on the left-hand side, this is the situation we actually have. This is what it means for a node to be reachable. It lies on a path PI. Path PI goes from S to TI, the sink of the commodity. And on this subpath here, from S to V, we have the property that flow Y is at least flow XA. This actually means if we remember what we actually want to show, we want to have lower bounds of XA minus the maximum demand. If we have a subpath that actually has flow at least XA, it means that independently on which commodity we have here, we can reroute the demand from this subpath here without violating the lower bounds we want to get. So this is actually what this augmentation step does. So we reroute from this SV subpath we have along an arbitrary path from S to V, which I denote back here. This is actually one that has been shown here. And now what we get is a new unsplittable flow as we've changed the path we were using for commodity I. And now the demand DI is routed along this arbitrary subpath Q. And from V to TI, we use the same subpath as before. So this results in a new unsplittable flow. And additionally, we have the information that along those arcs here, we do not have new violating arcs. Violating arcs means in this case that it might go below this this lower bound we want to have. So we do not like create new violating arcs. We can only make it like better. And just for the notation, I use this arrow here. You can see it on the right-hand side below. If there exists a finite sequence of such augmentation steps from y to y prime. So we're starting with y, and if I have this notation, there is a finite sequence of such augmentation steps leading us to y prime. Okay, I hope those augmentation steps are clear, because this is very important for what is following. So just to make it clear for everyone, we always reroute from subpaths that have enough flow in some sense along arbitrary paths. Okay, so now we come to the key lemma, and the actual result, the theorem I've been presenting before, is a quite direct consequence of this key lemma. So the following slides are focusing on this key lemma, and then what is following is quite forward. We are showing now that for a given unsplittable flow, an arbitrary flow y, and a node v, there always exists such a finite sequence of augmentation steps, so that v is reachable with respect to this new unsplittable flow. I hope that this is clear. It means that every node, independently on which arbitrary unsplittable flow we have, every node is at some point reachable. And at some point reachable, actually, this is what I mean by eventually reachable. Okay, so this proof is by contradiction. We will assume that there exists an unsplittable flow y such that not all vertices are reachable. So this set of eventually reachable nodes is not the whole vertex set. Just to give you an illustration, so this is the set xy, and if a node is inside of the set, it means that there is a sequence, a finite sequence of augmentation steps, such that at some point this node is reachable, which means that we have it lies on some path, and along this blue subpath we have the property that the flow of the unsplittable flow is at least the flow of the given fractional. Okay, this set is quite interesting, and it can only decrease, because whenever, if I compare now y to y prime has been obtained by a finite sequence of augmentation steps applied to y. So if a node is an xy prime, then it is eventually reachable starting from y prime, so automatically it's eventually reachable starting from y. So what we can do now is choose y in such a way that this set is inclusion-wise minimal, which means that it does not change anymore, and we can actually denote it by x, because it does not depend anymore on the sequence of augmentation steps we apply to the unsplittable flow we have. And what is very important for what follows is that those augmentation steps actually cannot decrease the outgoing flow of this set. Whenever we reroute, we decrease on a like sequence of arcs, and all those nodes lying on this subpath here are reachable at this point. Otherwise, we cannot decrease flow along those arcs. So we cannot reroute a demand that is routed this way, so exiting and entering X again. So we cannot decrease arcs flow on any arc exiting X. Okay, so what we do now is that we choose Y in a way that not only X is inclusion-wise minimal, but also that the outgoing flow is maximal. This is the situation we have now, and now there are two nice properties we will have a look at. First of all, we can show now that there aren't any incoming arcs of x. If there was such an arc, and we know that this node here is eventually reachable. So at some point, we can apply a sequence of augmentation steps leading to this situation that we have this y prime, the node v lies on this path, and on the subpath, we have this nice property. But now we might simply choose an arbitrary path exiting x and using this arc here. It means that rerouting from this subpath here along this arbitrary arc we've chosen, we might increase the outgoing flow. And this contradicts this assumption of maximality. This first property actually implies that there is an outgoing flow, outgoing arc used by a commodity, so YA is strictly positive, and flow YA is at least flow XA. This is a quite direct consequence of the first property, as we do not have any incoming arcs, and both flows X and Y satisfy the same demands. We actually have such an arc because all those outlying commodities has to be satisfied by Y as well. I hope that this is clear so far. Now I use a fact that is, like, I do not want to go into details of the proof. It's a bit technical and it's not this interesting. But what we can show is that if a node lies in X, so it's a node that is always eventually reachable, and it lies on a path Pi for some commodity, then V is actually eventually reachable for the specific commodity with respect to Y. And this becomes very important in what follows. So we have this arc A. Remember the second property we've just seen. So A with a starting node V, so A is VW, V is the one lying in X here, and it's an outgoing arc lying on a subpath on a path Pi for some commodity I, such that its flow value Y is at least XA. Now we use this fact for this node V. We know that it's eventually reachable. So it lies in X, and it lies on path Pi by how we've picked arc A. So it is eventually reachable for commodity I. What does it mean? It means that there exists a Y prime obtained by a sequence of augmentation steps starting from Y, so that now V lies on this path we've chosen for commodity I, and such that for this subpath from S to V, we have this property that Y prime is at least X. Now notice that we cannot decrease flow on arc A. This is what we've seen before. And actually, we cannot increase it either, but this is not what is important here. So the important part is that flow cannot have been decreased by applying those augmentation steps going from Y to Y prime. So Y prime A is now still at least XA, which means that now this node W actually is reachable. And this contradicts the fact that it's lying outside of X. This gives us the contradiction we wanted to have. And now to just get back to the key lemma, what have we seen? So we've seen that independently on which unsplittable flow we're starting with, every node is eventually reachable. So for every node, there's a finite sequence of those simple augmentation steps, leading us to a new unsplittable flow Y prime, such that now this node we've chosen is actually reachable with respect to Y prime. Okay, I hope that you're still with me. Now we're having a look at this quite easy corollary. So what we can actually show now with this key lemma is that for a given flow Y and a chosen arc, we can always somehow augment flow on this arc until we have a lower bound of XA. So there always exists a finite sequence of augmentation steps leading to this unsplittable flow Y prime, such that now Y prime A is at least XA. This is actually a quite direct consequence of this key lemma. We might, for example, assume by a contradiction that there is such a flow such that even though I have a look at the flow that has maximum, at the unsplittable flow that has maximum flow value on this arc, it might not be large enough. We can still, if we have this arc and we look at the head node of this arc, we can make this arc by the key lemma reachable. And this means that we can reroute again flow along this arc A, which contradicts the maximality we might have assumed. So this is a quite easy follow-up of the key lemma we've just seen. Okay, so let's come to the theorem. So what do we want to show? We want to show that for a given flow X, there is an unsplittable flow Y such that arcwise, there's an arcwise lower bound of XA minus the maximum demand for all arcs. What we can do now is we start with an arbitrary unsplittable flow. Everything we've seen so far is for arbitrary flows. And now we apply the corollary at each arc successively. So we start with an arbitrary flow. We pick an arc and we apply the corollary so that at the next step with a new unsplittable flow, we have this lower bound, satisfy the lower bound that is given in the corollary. And if we go through all arcs now successively, then we're actually done, because whenever we've hit this bound of XA once, we might still decrease the flow by demand, but we only decrease the demand on arcs that have actually enough flow. So if I have a flow at least XA and I remove like one demand that is rerouted along this arc, we will never like violate this lower bound here. Okay, and this can all be done with this very simple augmentation step that we've previously seen.
So you have 5 more minutes.
Okay, perfect. We will quickly come to those arcwise lower and upper bounds. We will first have a quick look at the special case, which can be done by iterative rounding procedure, which has already been used by Koleopoulos and Stein in 2002 and by Scutella in 2002. They've actually only looked at the upper bounds, and what we could show is that with a similar procedure, we can actually have lower and upper bounds simultaneously in the special case where all demands are integer multiples of each other. And then we solve the general case by rounding down the demands. This is why we actually lose a factor of 2 here. I will not go into details there. It's yeah, it's kind of quite forward to get to the general case with those slightly looser upper and lower bounds. Okay, so we consider flow X satisfying those demands. They all are integer multiples of each other. And what we will use is this classical results that if all the demands are integral, then a flow can be turned into an integral flow such that its value on all arcs lies between the integer part and the integer part plus 1. The procedure works as follows. So we start with flow X. We successively choose STI paths, and then we decrease the flow and delete this commodity we've already been routing. So first of all, we turn X into a d-min integral flow. So d-min is the minimum demand. This flow actually does not differ by too much. It differs by at most the minimum demand. And this is what we will successively apply to X. So now we can route each demand of value dmin unsplittably. We simply choose a flow carrying STI path, and then we decrease the flow along PI and delete the commodity. And this is how we put together the unsplittable flow. We just save the flow carrying paths we've chosen, and in the end, its flow values differ by at most dmax minus dmin. For the general case, we simply round down the demands, and then we apply the above mentioned procedure. As I said, this is why we lose a factor of 2. Okay, some concluding remarks. Here you can see the results. We have focused on the first part in this talk, and I quickly went through the proof ideas of the second part here. Some open questions, first of all, regarding the flows with arcwise lower bounds. We do not have any efficient strategies so far for applying those augmentation steps. So in particular, we do not know how to bound the length of those sequences. So it's an existing result, but we do not have an efficient algorithm so far. This is something we would like to work on. Regarding flows with arcwise low and upper bounds, of course, it would be nice to have like an extension of those proof ideas I've presented to you. So can we find a proof using some kind of augmentation steps similar in spirit to what we've seen so far? And do those tighter bounds also hold in the case of arbitrary demands? This would be very interesting. And just to conclude, what we conjecture, what we would like to see proven is that even with arbitrary arc costs, this is kind of an extension of what we've seen so far. So given those arc costs and the flow X, showing that there is an unsplittable flow Y such that the cost is at most the cost of the given flow, and such that those tight upper and lower bounds are shown, are satisfied. This would be really nice. And this is actually a strengthening of Gumann's conjecture from 2000. He was actually interested in upper bounds, so the part with the lower bounds is missing in this conjecture. And this is why we formulated the strengthening, because it might be very interesting to really have simultaneously lower and upper bounds. Thank you.
Thank you, Sarah, for the very nice and clear talk. Are there any questions from the audience? I don't see any. So let me check once more. Then I have a quick question. You considered single source. How about two or multiple sources? Do you know anything?
So we didn't have a look at it. Don't think that, I think those augmentation steps might be too easy in structure to work, but we should have a closer look at it. I cannot say it like right now.
Okay, so if there are no further questions, then I unmute all of you and let's clap our hands for